Precious and welcome to the section of Grade 9 CBSE Maths class. Today we are looking at the chapter number 1, Number System. First chapter of Grade 9 CBSE Mathematics, that is Number System. Chapter number 1, its name Number System. Already you are aware of how numbers are classified and the criteria we used to classify the numbers. We are having different classification of numbers as natural numbers, real numbers, integers, and irrational numbers, whole numbers, etc. etc. Here in this chapter, first we have to discuss about different classification of numbers on the basis of a real number line. Then from this classification, we will go through problems related to the classification. How we can find the rational numbers in between two numbers, or how we can find irrational numbers between two numbers, or how we can locate root numbers in a number line, and how we can operate to rational or irrational numbers, and how we can solve problems using identities. These all are going to discuss in this chapter, number system. First of all, I would like to introduce the number line to you. Already you know how a number line looks like or how a number line can be interpreted. Just as a basic, I will start with that same number line. Yeah. Just look, consider this as a number line. You know that in a number line, the center of the number line is the 0. The center of the number line is the 0. Towards the right of the 0, there are positive numbers. Towards the right of the 0, there are positive numbers. Then towards the left of the 0, there are numbers called negative numbers. There are numbers called negative numbers. That is, when we are walking on a number line from 0 towards right, we get positive numbers. But when we are walking towards the left of the 0, we only get negative numbers. That is, 0 is the center of the number line. From 0 towards right, it is counted as positive. That means 1, 2, 3, 4, 5, etc. etc. And from 0 towards its left, we count as -1, -2, -3, -4, -5, etc. etc. This is a real number line. Now I am going to mark 1, 2, 3, 4, 5, etc. Towards the left, it is -1, -2, -3, -4, -5, etc. And this is how a number line looks like. By considering this number line, I am going to define natural numbers, whole numbers, integers, and rational numbers. I am going to define natural numbers, whole numbers, integers, and rational numbers. Now let us look from this number line how we can define this classification of numbers. Now 0 is the center of the number line. I am marking the center of the number line is 0. When I am walking towards the right, just think you are walking towards the right of the 0 and you are carrying a bag with you. When you are walking, you first pick one from there here and put it in your bag. And towards in front of one, there is two, you pick it and put it in your bag. Like the similar way, when we are walking towards and we are picking 1, 2, 3, 4, 5, etc. and put these together in a bag. Consider this is the bag. We are picking 1, 2, 3, 4, 5, etc. Now we get a bag full of numbers including 1, 2, 3, 4, 5, etc. Then this bag contains numbers of natural numbers. Now this bag contains numbers of natural numbers. Clear? It is natural numbers. Okay. Now how we will define natural numbers? Natural numbers can be defined as the numbers starting from 0 and going to, starting from 1 and going towards the right as positive. They are called natural numbers. Clear? When we are going towards right of 0, we get only positive numbers. From 1, I am picking 1, 2, 3, 4, 5, etc. and put together in a bag. Then we can say that this bag consists of natural numbers. This bag consists of natural numbers. This is our first classification, that's called natural numbers. Now I came back and put the center of the number line 0 and pick this 0 and put it in the same bag. I am taking this 0 as well and put the 0 in the same bag. Now the bag consists of natural numbers plus 0. Now the bag consists of 1, 2, 3, 4, 5, etc. are called natural numbers, and then I take 0 from the number line and put the same 0 in the bag. Now the bag consists of natural numbers. Additionally, a 0 is there. That means a 0 plus remaining natural numbers. 0 plus these natural numbers are togetherly called as whole numbers. 0 plus these natural numbers are togetherly called as whole numbers. That means 0, 1, 2, 3, 4, etc. etc. are known as whole numbers represented by W. Natural numbers can be represented by using the letter, capital letter N, alphabet N. Now whole numbers can be represented using W. That's what called whole numbers. That means when we are picking only positive numbers right of 0, that is 1, 2, 3, 4, 5, etc. We are not taking 0. Except 0, we are taking 1, 2, 3, 4, 5, etc. etc. Then that numbers are togetherly called as natural numbers. That means 1, 2, 3, 4, 5, etc. up to positive infinity. Then if we take 0 and then put the same 0 with the same bag as we collect the natural numbers, then 0 plus these natural numbers can togetherly called as whole numbers. That means 0, 1, 2, 3, 4, 5, etc. are togetherly called as whole numbers represented by the letter W. Now, when I look at the number line, we pick 0, 1, 2, 3, 4, 5, etc. towards the right, towards the positive infinity. But when we look again, we are observing that -1, -2, -3, -4, -5, etc. These negative numbers are remaining in this number line. Now I take all these numbers and put these numbers in the same bag where 0, 1, 2, 3, 4, etc. are there. Now I expand the bag and put -1, -2, -3, -4, etc. to the same bag. Here, now this bag consists of -1, -2, -3, -4, etc. up to negative infinity, 1, 2, 3, 4, 5, etc. up to positive infinity and 0. That means negative numbers, positive numbers and 0 are there in this bag. Then these numbers can be togetherly called as integers. Then these numbers can be togetherly called as integers. That is positive numbers, negative numbers and 0 togetherly called as integers. This positive number can also be called as positive integers. If you saw positive integer in a textbook or in your question paper, then the positive numbers, positive integers 1, 2, 3, 4, 5, etc. Then remember, if you saw positive integers, then it is same as the natural numbers, that is 1, 2, 3, 4, 5, etc. When you are seeing negative integers, then it is -1, -2, -3, -4, -5, etc. And you are seeing only integers represented by the letter Z, then we can say that all the positive numbers, all the negative numbers and the 0 togetherly constitute integers represented by Z. Now we completed 3 classifications: natural numbers, whole numbers and integers. What is natural numbers? 1, 2, 3, 4, 5, etc. up to infinity are togetherly called as natural numbers. If we are putting a 0 to these natural numbers, then it becomes the classification of whole numbers, that is 0, 1, 2, 3, 4, etc. up to infinity. Again, if we are putting the negative numbers towards this classification, then it becomes integers, that is all negative numbers, positive numbers and 0 togetherly called as integers represented by the letter Z. Now we are having more classification. One among them is next, a rational number. What do you mean by rational number? Here in this number line, look, we are considering -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, etc. But in between these numbers, for example, in between 1 and 2 there is 1.5. In between 2 and 3 there is 2.5. In between 3 and 4 there is 3.5. Like the similar way, in between -2 and -3, -2.5, -2.6, -2.7. That means in between the whole numbers, fractions are also there. That means 1/2, 1/3, 1/4, 1/5. Like fractions are there in between whole numbers. If we are including these fractions towards this bag, I am expanding the bag again and I am adding this 1/2, 1/3, 1/4, etc. Then it becomes whole numbers. Then it becomes whole numbers in the number line. That's what called rational numbers denoted by the letter Q. Then it is called rational numbers denoted by the letter Q. Okay, clear? That is, now we can define rational numbers as all negative numbers, positive numbers, 0, including the fractions. That means those numbers which can be expressed in the form P by Q. Those numbers which can be expressed in the form P by Q. Only numbers which can be expressed in the form P by Q are called rational numbers, where P and Q are integers and Q not equal to 0. Such numbers are called rational numbers. Clear? Rational numbers are the numbers which can be expressed in the form P by Q, where P and Q are integers. where P and Q are integers and Q not equal to 0. That means denominator not equal to 0. If denominator equal to 0, then it becomes not defined or infinity. The value cannot be defined. Therefore, denominator does not be 0. That is Q not equal to 0. Then rational numbers can be defined as numbers which can be expressed in the form P by Q. Numbers which can be expressed in the form P by Q, where P and Q are integers and Q not equal to 0. This is the condition for natural numbers. That means the numbers in this number line, all whole numbers, can be written in the form of P by Q. That is, 1 can be written as 1 by 1, 2 can be written as 2 by 1, 3 can be written as 3 by 1, or 5 can be written as 5 by 1, minus 5 can be written as minus 5 by 1, minus 10 can be written as minus 10 by 1. That means the numbers in this number line can be expressed in the form of P by Q. That means in a fractional form. Then these numbers are called as rational numbers. That means all natural numbers can be expressed as natural numbers. Clear? That's what called rational numbers. Now we go through 4 classifications of numbers: natural numbers, whole numbers, integers, and rational numbers. Now recollect what is natural numbers: 1, 2, 3, 4, etc. up to infinity. Then whole numbers, if we put a 0 together towards with natural number, then these natural numbers and 0 togetherly called as whole numbers. And again we are putting the negative numbers towards the same classification. That means natural numbers, 0, and the negative numbers are togetherly called as integers. Then in between the whole numbers there are fractionals also. If we are considering these fractions too, then the whole classification is called rational number. And one important thing regarding rational number is that the number which can be expressed in the form P by Q. That means rational numbers can also be always expressed in the form P by Q, where P and Q are integers and Q not equal to 0. Q is the denominator. If denominator equal to 0, then the value is not defined. That's why we are always saying that in a rational number, the denominator does not be 0. That is Q not equal to 0. Now, with this rational number, we are having problems. That means in your textbook, it is in the first exercise. Now the first section is completed and we are going to look at some problems of your first exercise. That is first chapter, exercise number 1. That is, I think in your textbook it is 1.1. To find rational numbers between two numbers. Now look at a question. The question is that find 5 rational numbers. Find 5 rational numbers between 1 and 2. This is the question. Find 5 rational numbers between 1 and 2. How will you find 5 rational numbers between 1 and 2? That means rational numbers are numbers which can be expressed in the form P by Q. We need the rational numbers between 1 and 2. Between 1 and 2 means neither 1 nor 2 can be taken. In between 1 and 2, the numbers are taken. Then look how we can solve this problem. This problem can be solved in two ways. We are having two methods to solve this problem. That means if you are asking 5 rational numbers or 10 rational numbers or 15 rational numbers or 20 rational number between any two whole numbers, then you can find the solution using two methods. In general, we can say that find n rational numbers between x and y, where x and y are whole numbers. This is the general form. Find n rational numbers between x and y, where x and y are whole numbers. Here n is equal to 5, x and y are 1 and 2 respectively. Okay. Then the method 1, first method is method 1. First method is that in between 1 and 2, we have to find 5 rational numbers. If we are giving two whole numbers, that is, if R and S are two whole numbers. If R and S are two whole numbers, then R plus S by 2 is in between R and S. Then R plus S by 2 is in between R and S. Clear? If R and S are two whole numbers, then R plus S by 2 is in between R and S. Here 1 and 2 are whole numbers. Then 1 plus 2 by 2, that is equal to 3 by 2 is in between 1 and 2. This is the first one. This is one rational number between 1 and 2, 3 by 2. Now we can write 1, 2. In between 1 and 2, there is 3 by 2. Now, consider two numbers as 1 and 3 by 2. Now, 3 by 2 is not a whole number. Just consider this as numbers. 1 and 2 are whole numbers. That's why I write if R and S are two whole numbers, then R plus S by 2 is in between R and S. Here, we are considering 1 and 3 by 2 again. 3 by 2 is not a whole number. Then 1 plus 3 by 2 by 2 is in between 1 and 3 by 2. That is 1 plus 3 by 2 by 2 is 2 into 1, 2. 2 plus 3, 5. That is 5 by 2 by 2. Any fraction divided by another number, we can use the cross multiplication method. That is 5 by 2 divided by 2 is equal to 5 by 2 into 1 by 2. That is 5 by 4. That means 5 by 4 lies between 1 and 3 by 2. That is same as 1 and 2. Again, consider this 3 by 2 and 2. Consider this 3 by 2 and 2. Then 3 by 2 plus 2 by 2 is in between 3 by 2 and 2. That is 2 into 2, 4. 4 plus 3, 7. 7 by 2 whole divided by 2. That is equal to 7 by 4. 7 by 4 is in between 3 by 2 and 2. That is in between 1 and 2. Now look. In between 1 and 2, we get 3 rational numbers, 5 by 4, 3 by 2 and 7 by 4. Again, we can consider 1 and 5 by 4 are two numbers. Then 1 plus 5 by 4 divided by 2 gives a rational number in between 1 and 5 by 4. Then consider 5 by 4 and 3 by 2. Then consider 5 by 4 and 3 by 2. Then 5 by 4 plus 3 by 2 divided by 2 gives a rational number between 5 by 4 and 3 by 2. Then consider 3 by 2 and 7 by 4. Then 3 by 2 plus 7 by 4 divided by 2 gives a rational number in between 3 by 2 and 7 by 4. Again, continuing this process, we get infinite number of rational number between two numbers. That means in between 1 and 2, we can find 5 rational numbers, 10 rational numbers, 20 rational numbers, 100 rational numbers, etc. up to infinity. That means there are infinite rational numbers between two numbers. This is the first method. We are solving this again and again using r plus s by 2. That means consider two numbers, then add these two numbers, divided by 2 gives the rational number in between these two. Again, continuing this step, we get more and more rational numbers in between the two numbers. Now, we are having another method. That means in one step, we get all the rational numbers in between the two numbers. That's the second method. Here, we are solving this step by step. In step 1, we get one rational number. Again, step 2, we get another rational number. Again, step 3, we get another. Like in step by step, we get all the rational numbers. But in second method, we get all the answers in one step. We get all the answers in one step. That is method 2. Second method. In second method, for n rational numbers between x and y, if we are asking to find n rational numbers, then take the number that is n plus 1. If we are asking n rational numbers, then take the number n plus 1. Here, find 5 rational numbers. That's the question. Therefore, take 5 plus 1 is equal to 6. That means 1 and 2 are the numbers. We need 5 rational numbers in between 1 and 2. We need 5 rational numbers, therefore we take 6. If we need 10, we have to take 11. If we need 20, we have to take 21. That means for n rational numbers, we have to take n plus 1th number. That is 5 plus 1, 6. Put this 6 as the denominators of both given numbers. For 1, how it becomes 6 as denominator? 1 can be written as 6 by 6. Now we get the denominator as 6 and value is 1. And 2 can be written as 12 by 6. Denominator is 6 and 12 by 6 is 2. Value remains the same, doesn't changes. 6 by 6 is 1 and 12 by 6 is 2. For 5 rational numbers, we are making the denominator as 5 plus 1, that is 6. If we are asking 10 rational numbers, then make the denominator as 10 plus 1, 11. If we are asking 15 rational numbers, then 15 plus 1, 16. That should be the denominator. Now here in this question, it is 5. Therefore, I made the denominator as 6. That is 6 by 6 is 1 and 12 by 6 is 2. Here we get 6 by 6 and 12 by 6. 6 by 6 is 1 and 12 by 6 is 2. Now we can write the rational numbers in between them as 7 by 6, 8 by 6, 9 by 6, 10 by 6, 11 by 6 and 12 by 6. 6 by 6 is 1 and 12 by 6 is 2. In between them, there is 5 rational numbers, 7 by 6, 8 by 6, 9 by 6, 10 by 6, 11 by 6. Not 5, we can write infinite number of rational numbers. Here only 5 number is needed. Therefore, we take the denominator as 6. Then we get 5. Clear? This is the second method. In one step, we get all the answers. That means find 5 rational numbers between 1 and 2. That is 7 by 6, 8 by 6, 9 by 6, 10 by 6 and 11 by 6. These are all rational numbers in between the values of 1 and 2. Now we can check if it is correct or not. I am dividing 9 divided by 6. 1 into 6, 6. Remainder 3. 3 divided by 6 is not possible. Putting a point. Then it becomes 30. 5 into 6, 30. That is 9 by 6 is 1.5. Which is in between 1 and 2. No doubt. Now consider 10 by 6. 6 into 1, 6. Remainder 4. 4 divided by 6 is not possible. Putting a point. 0. 6 into 6, 36. Remainder 4. 40. 6 into 6, 36. Remainder 4. That is 1.6666, etc. 1.6666 in between 1 and 2. Like the same way, we get all the rational numbers in between two numbers. This is the second method. I think it's clear to you. We can solve one more question from the same topic. Find four rational numbers between not four. We just did five rational numbers. We can take 7 rational numbers between find 7 rational numbers between 1 by 2 and 3 by 4. Now, the numbers are 1 by 2 and 3 by 4. Okay, the numbers are 1 by 2 and 3 by 4. We have to find 7 rational numbers in between 1 by 2 and 3 by 4. For n rational numbers, we should take n plus 1 as denominator. Here we need 7 rational numbers. Therefore, 7 plus 1 is equal to 8 should be the denominator. We have to make the denominators of both the fractions as 8. How 1 by 2 becomes 1 by 2? To change it as denominator 8, 2 into 4, 8. Then multiply the same 4 in denominator, then it becomes 4 by 8. How 3 by 4 can be changed to a number whose denominator is 8? 4 into 2 is 8. Then 3 into 2 is 6. Right. Now look, 4 by 8 and 6 by 8. In between, we are having 5 by 8. Clear? One rational number we get. 4 by 8, 5 by 8 and 6 by 8. We get one rational number. Okay. Now, use the same method as the first one. In between these two, we can find one more rational number by 4 by 8 plus 5 by 8 whole divided by 2. 4 by 8 plus 5 by 8 whole divided by 2. We get a rational number in between them. Then 5 by 8 plus 6 by 8 whole divided by 2. We get a rational number in between these two. Then the same process continues. We get 7 rational numbers. Clear? In this method, I use the n plus 1 formula, that is n plus 1 8. But when we are using here, we get only one number between 4 by 8 and 6 by 8, that is 5. So, in this case, if we are solving a question, if we are getting less number than the required one, then use the first method club to the second method. Just collaborate the first and second method. That means considering these two, 4 by 8 plus 5 by 8 divided by 2 gives a rational number in between these two. 5 by 8 plus 6 by 8 divided by 2 gives a rational number in between 5 by 8 and 6 by 8. Thus, we can find more number of rational numbers in between two numbers. Now, we can go through one more problem. Find 9 rational numbers between 5 and 6. The numbers are 5 and 6. We need 9 rational numbers, that is 9 plus 1 is equal to 10 should be the denominator. How 5 can be made to a number, changed to a number whose denominator is 10? That is 50 divided by 10 is 5. You all know. Then 6, 60 divided by 10 is 6. You all know. Okay. Now you write 9 numbers in between. 51 by 10, 52 by 10, 53 by 10, 54 by 10, 55 by 10, 56 by 10, 57 by 10, 58 by 10, 59 by 10, and 60 by 10. Now you get 9 rational numbers in between 5 and 6. Here in this problem, only second method is needed. We get all the 9 rational numbers. That is why how we found rational numbers in between two numbers. The general form is that to find n rational numbers between x and y. For first method, x plus y divided by 2 gives a rational number between x and y. Then same step continues and we get all the rational numbers. In the method 2, for n rational numbers needed, take n plus 1 as denominator. Then we get the rational numbers in between that two numbers. I think now it's clear to you. Natural numbers, whole numbers, integers, and rational numbers, and how to find rational numbers between two given numbers. Okay. Now we already discussed about natural numbers, integers, whole numbers, and rational numbers. Now we have another set of classification called irrational numbers. What do you mean by irrational numbers? We know that rational numbers are numbers which can be expressed in the form p by q, where p and q are integers and q not equal to 0. For an irrational number, the numbers which cannot be expressed in the form p by q, that means irrational numbers cannot be expressed in the form p by q, where p and q are integers and q not equal to 0, conditions are same. These numbers cannot be expressed as fractions. Simply we can say that irrational numbers cannot be expressed as fractions. Only rational numbers can be expressed as fractions, that is of the form p by q, where p and q are integers and denominator should not be 0. If it is 0, the value is not defined or infinity. Therefore, in rational numbers, it is of the form p by q. This is the form. But for irrational numbers, it cannot be expressed as p by q. The numbers which cannot be expressed in the form p by q are called irrational numbers. Now we can differentiate between rational and irrational numbers. The numbers which can be expressed in the form p by q, where p and q are integers and q not equal to 0, are called rational numbers. On the other hand, the numbers which cannot be expressed in the form p by q are called irrational numbers. For example, root 2, root 3, root 5, root 7, root 10, etc. are called irrational numbers. These numbers cannot be expressed in the form p by q. These root 2, root 3, root 5, root 7, root 10, etc. cannot be expressed in the form p by q. Now, how will you show root 2 is irrational or root 3 is irrational or root 5 is irrational? I directly say root 2 is irrational or root 3 is irrational or root 5 is irrational. How will you believe this is irrational? We have a proof, but you need not worry. You study the proof in next class, that is 10th standard. Only in 10th grade, you need to study the proof of root 2 is rational or root 3 is rational. That's a question. That's a board question, board exam question in 10th standard maths. So now you need not worry. You just remember root 2, root 3, root 5, root 7, root 10, etc. is irrational. Okay. But you are having a question from this topic as locate root 2 on the number line, or locate root 3 on the number line, or locate root 5 on the number line, or locate root 7 on the number line. You don't know where is root 2 or root 3 on the number line. We only know that 0, 1, 2, 3, 4, 4 minus 1, minus 2, minus 3. In between 1 and 2, there is 1.1, 1.2, 1.3, 1.4, etc. But where is root 2 or where is root 3? In a number line, how will we accurately mark root 2? Not we need a rough figure, we need the accurate point in which root 2 lies. That's a question for your exam. Locate root 2 on the number line. Now, before going to locating root 2, I should say a term called Pythagoras theorem. Don't you remember this theorem, Pythagoras theorem? This is an important theorem in mathematics. You already studied the theorem, Pythagoras theorem. I just want to recollect what's in your mind about Pythagoras theorem. This is the theorem connecting the relations between hypotenuse, base, and altitude. Simply, the theorem is hypotenuse square is equal to base square plus altitude square. For a right angled triangle, only in right angled triangle, Pythagoras theorem can be applied. For a right angled triangle, when we are considering a right triangle, this is the right angle. Opposite to right angle is the hypotenuse, and this is the base, and this is the altitude. Now the relation is that hypotenuse square is equal to base square plus altitude square. The relation is that hypotenuse square is equal to base square plus altitude square. This is the Pythagoras theorem. Now you will be in a bit confusion. I am discussing about irrational number. Then why I am explaining Pythagoras theorem here? Because to locate root 2 on a number line, we need to know the Pythagoras theorem. That's why I just recollect what Pythagoras theorem is. Now we can locate root 2 on number line. This is the question. The question is locate root 2 on the number line. Before considering the number line, first of all, I'm explaining how we find the length of root 2 or the value of root 2. Okay. Just consider a square. Just consider a square of unit length. Just consider a square of unit length. I'm naming it as A, B, C, D. A, B, C, D is a square of unit length. The length is unity. Okay. Now I'm drawing a diagonal. Yes, this is the diagonal. Now we get a right triangle ABC. Consider the right triangle ABC. This is our right triangle. In this triangle ABC, ABC is the right triangle. We are applying Pythagoras theorem to this triangle to find the hypotenuse AC. We are applying Pythagoras theorem to this triangle ABC to find AC. Then Pythagoras theorem is hypotenuse square is equal to base square plus altitude square. Hypotenuse square is equal to base square plus altitude square. Here AC is the hypotenuse. Therefore, AC square is equal to AB is the base. AB square plus BC is the altitude. BC square. That is AC square is equal to AB square plus BC square. That is AC square is equal to AB is unity, that is value is 1, 1 square plus BC is also unity, that is 1, value is 1 square. Then AC square is equal to, we know that 1 square is 1 plus again 1 square is 1. AC square is equal to 1 plus 1, 2. This is AC square. To find AC, we have to take the square root. That is AC is equal to root 2. This is root 2. Now we get root 2. This is the value of root 2. From A to C, this is the length of root 2. This is the value of root 2. Now you should understand how root 2 can be found out. The question is, locate root 2 on the number line. We now know that how root 2 can be found out. Then we have to locate it on the number line. So we have to draw the same square on the number line, the same unit square on the number line. Now I am going to draw the same unit square on the number line and locate root 2 on the number line. Let us consider a number line. This is our number line. On the center there is 0, then 1, 2, 3, etc. Towards left -1, -2, -3, etc. We have to consider the same unit square on this number line. That is, I am going to consider the unit square on the number line. Yeah, this is our unit square having unit length and breadth. Now we have to draw the diagonal of the unit square. The name as A, B, C and D. Now this is the length of root 2. We already know that this is the length of root 2. Now how will you locate this on the number line? Now one more thing, you can easily draw it from 0 to 1. That's simple. Same square can be, no problem whether it is 1 to 2 or 2 to 3, then that length can be drawn from 0 because 0 is the origin. So for easy purpose or so for easy calculation, I am drawing the same figure from 0 to 1. And this is the value of root 2. Now what you have to do is just take a compass from your instrument box and put the pointed end in 0 and put the pencil in this length root 2 and then draw an arc like this. Where the arc meets the number line, there lies the root 2. There lies the root 2. Clear? Put a compass, place it like this and then draw an arc like this. Where the pencil points on the number line, there lies root 2. Now, I think it's clear to locate a root 2 a number line. I should solve few more questions to make it easy for you. Now locate root 3 on number line. Locate root 3 on number line. How will you locate root 3? We know that when we are considering a unit square, then the diagonal of the square gives root 2. Clear? This is one, this is one. Okay. Now I am taking only that right triangle. I am taking only that right triangle. This is our right triangle where base and altitude are unity 1. Then the hypotenuse is root. Clear? Then I am taking a unit length from here. From here I am taking a unit length, making an angle 90 degree. Now completing the triangle. Now completing the triangle. I'm naming it as A, B, C and D. Now look, you get another right triangle ACD. This is unity. By considering the same right angle triangle from the unit square ABC, this is our required right angle triangle. We know that base is unity, altitude is unity, then hypotenuse is root 2. Now I draw a unit length taking 90 degree from C and completing this as a triangle. We get another right triangle ADC. Okay, in triangle ADC. Again, I am taking Pythagoras theorem, that is hypotenuse square is equal to base square plus altitude square. Here the hypotenuse is AD, that is AD square is equal to CD square plus AC square. That is AD square is equal to CD is 1 square plus AC is root 2, that is root 2 square. That is AD square is equal to 1 square, that is 1, root 2 square is 2. Therefore AD square is equal to 1 plus 2, 3. AD square is equal to 3. Therefore AD is equal to, taking the square root, we get root 3. That is AD is equal to root 3. Then draw this on the number line. 0, 1, 2. Minus 1, minus 2. Then we are considering okay, this is 1, this is 1 and this is root 2. And now we are taking a unit length and completing it into a square. Then this is 1, then root 2 and 1, then this is root 3. Now put a compass like this and draw. This is root 3. Put a compass and draw an arc like this. Then it meets the number line in root 3. Thus, how will you locate root 3 on the number line? On the similar way, we can locate root 5. I will show how root 5 is located. Then you have a work to do root 7. Okay. Now locate root 5. Am I considering not a square, it's a rectangle. This is 2 and this is 1. Considering a diagonal. I am taking this triangle as this is 2 and this is 1. Now apply the same Pythagoras theorem. ABC, that is AC square. Pythagoras theorem, AC square is equal to ab square plus bc square, that is ab square, that is 2 square plus bc is 1 square. 2 square you know that it is 4, 1 square is 1, that is 5. Therefore ac square is 5, ac is equal to root 5. Draw the same thing in a number line and this is root 5. Locate this on the number line. On the same way you can locate root 7. Root 2, root 3, root 5 or root 7. From these four, any one of them is asked in the exam of your board. So root 2, root 5 and root 7. Okay, I think it's clear to you how to locate irrational numbers. That means root 2 or root 5 on the number line. Okay. Now we discussed about natural numbers, whole numbers, integers, rational numbers and irrational numbers. These rational numbers and irrational numbers are togetherly called as real numbers. Rational numbers and irrational numbers are togetherly called as real numbers. Then in the classification of real numbers, all rational and irrational numbers are there. Now we are going for another topic, decimal expansion of real numbers, that is decimal expansion. Our next topic under concern is decimal expansion. Decimal expansion. How will you expand a decimal? Just look one case, 1 by 3. How will you find the decimal expansion of 1 by 3? Just divide 1 by 3. We can look 1 divided by 3. 1 divided by 3 is not possible. Therefore, putting a decimal, then it becomes 10. 3 into 3, 9. Remainder 1. Again it becomes 10. 3 into 3, 9. Remainder 1. Again it becomes 10. 3 into 3, 9. Remainder 1. Again this continues on. That is 0.3333, etc. This continues like a series. This is the decimal expansion of 1 by 3. This is the decimal expansion of 1 by 3. Now look at another one, 7 by 8. 7 by 8. Just divide 7 by 8. 7 divided by 8. 7 divided by 8 is not possible. Putting a decimal, then it becomes 70. 8 into 8, 64. Remainder 6 becomes 60. 8 into 7, 56. Then remainder 4, it becomes 40. 8 into 5, 40. Remainder 0. That is 0.875. So decimal expansion of 7 by 8 is 0.875. Now look at another expansion, 1 by 7. 1 divided by 7. 1 divided by 7 is not possible. Therefore, putting a decimal, then it becomes 10. 7 into 1, 7. Remainder 3. It becomes 30. Then 7 into 4, 28. Remainder 2. It becomes 20. 7 into 2, 14. Remainder 6. It becomes 60. 7 into 8, 56. Remainder 4. It becomes 40. 7 into 5, 35. Remainder 5. It becomes 50. 10 into 7, 49. Remainder 1. It becomes, remainder 1, it becomes 10. Then 7 into 1, 7. Remainder 3, it becomes 30. 10 into 4, 28. Remainder 2, it becomes 20. 10 into 2, 14. And this continues like a pattern, that is 1, 4, 2, 8, 5, 7. again 142857 and repeated like this. Now look at the decimal expansion here. For 1 by 3 it is 0.33333 and continues like a pattern. For decimals continuing like a pattern, we can write 0.3 bar. This bar shows that 3 is repeating again and again like a series. Then 7 by 8, it is 0.875. No number is repeating again like a series, it is 0.875. Now 1 by 7, it is 142857, again 142857, that is 0.142,857. I'm giving a bar above the 142,857. That means 142,857 is again repeating. In these decimal forms, those numbers or those decimal expansions which are repeating again and again can be called as non-terminating recurring expansions. Non-terminating recurring means repeating. Therefore, 0.3 and 0.142857, these two are repeating again and again. That means 0.3333, 0.142857, 142,857, 142,857, again and again repeating. The decimal expansions repeating again and again like this are called non-terminating recurring expansions. Non-terminating recurring. That is, recurring means repeating. 142,857 is here repeating again and again. 0.3, 3 is repeating again and again. Therefore, these decimal expansions are called non-terminating recurring decimal expansions. Non-terminating recurring expansions. But here, look, the division is completed. 7 by 8, 0.875 is the answer. And the division is completed. No number is repeating again and again. 0.875. That's all. It is completed. Such expansions are called terminating expansions or terminating decimal forms. These are terminating decimal forms, and the repeating ones are called non-terminating recurring decimal forms. And I think it's clear to you what is terminating and non-terminating recurring. Okay. Now we can go through some problems related to this topic. First is show that this ST means show that 3.142678 this can be expressed as P by Q. That means this can be expressed as a rational number. How 3.142678 can be expressed in the form P by Q, or how we can express 3.142678 in form P by Q? That means it is a rational number. Now, how will you explain this on the basis of terminating or non-terminating recurring expansions? What is this? This expansion is terminating or non-terminating? This is terminating. No number is repeated again and again. If it is repeating in the question, it will be a number of dots here. But this is terminating. For terminating expansions, we can express it as rational form. How? This can be written as 3142678 divided by There are 1, 2, 3, 4, 5, 6 positions after the decimal. Therefore, 1, 2, 3, 4, 5, 6. Now look, 3, 1, 4, 2, 6, 7, 8 divided by 1, 10, 100, 1000, 10,000, lakh, 10 lakh divided by 10 lakh gives this number. Clear? There are 6 positions after the decimal. Therefore, divide it with 10 lakh. Then we will get this. You know that dividing it with 10, just put a dot from the right to left after one place. For dividing it with 100, just put a dot from the right side after two place. For 1000 it is 3 place, 10,000 it is 4, then 1 lakh it is 5, and 10 lakh it is 6. Then we get 3.14. This is the decimal form 3.142678 expressed in the form P by Q, or we proved it that 3.142678 is a rational number. Now, next question is express 0.3 bar in the form P by Q. This is a confusing question. Listen carefully. 0.3 bar in the form P by Q. We want to express 0.3 bar in the form P by Q. That is 0.3 bar can be expressed as rational form. How will we express this in the P by Q form or rational form? We know that 0.3 bar is equal to, when we are putting a bar above a number, that means the number is repeating again and again. 0.3 bar means 0.33333, etc. The number 3 is repeating again and again. Actually, we didn't know the value accurately. So, let x is equal to 0.33333, etc. That is 0.3 bar. Put 0.3 bar as x. Now, what I am doing is that here only one number is repeating again. Here only one number is repeating again. If only one number is repeating, then multiply both sides with 10. If two numbers are repeating again and again, then multiply both sides with 100. If three numbers are repeating again and again, then multiply with 1000. And so on. Here x is equal to 0.33333. Here only one number is repeating again and again. Therefore, I am going to multiply both sides with 10. Therefore, 10x is equal to 10 into 0.33333, etc. That is 10x is equal to 10 into 0.33 becomes 3.33333, etc. Now, 10x is equal to 3.333, etc. can be split into 3 plus 0.33333, etc. 3.3333 can be expressed as 3 plus 0.3333, etc. Okay, clear? Then 10x is equal to 3 plus 0.3333. This is what we represented as x. This is what we represented as x. That is x is equal to 0.3333. Therefore, in this position 0.33333, etc., we can write x. Now I am shifting this x to the left side, then it becomes negative. That is 10x minus x is equal to 3. 10x minus x is 9x. 9x is equal to 3. We want to find the value of x. That is value, the decimal form of 0.333. That is x is equal to 3 by 9. That can be simply written as 1 by 3. This is the rational form of 0.3 bar or P by Q form of 0.3 bar. Clear? Okay, now look at another question. Now, express 1.27 bar in the form P by Q. Listen carefully. 1.27 can be written as 1.27 bar can be written as, here the bar is above 2 and 7. That means both the numbers 2 and 7 are repeating again and again. That means 1.27, 27, 27, etc. 1.27 bar is equal to 1.27, 27, 27, etc. Now we have to find the P by Q form of 1.27 bar. Let X is equal to 1.27 bar. Okay. Here two numbers are repeating again. 2 and 7. Both the numbers are repeating again and again. That is 27, 27, 27, 27, etc. If one number is repeating again and again, we have to multiply it with 10. If two numbers are repeating again and again, we have to multiply it with 100. Therefore, I am multiplying here with 100. Then it becomes 100x is equal to 100 into 1.272727, etc. Clear? That is 100x is equal to 100 into 1.272727, that is 127.2727, etc. Then we can write 100x is equal to, now what I am going to do is 127.2727 is splitted as 126 plus 1.272727, etc. Now you know that 1.272727, etc. Here x is equal to 1.27 bar, that is 1.272727, etc. Thus 1.272727 can be written as x. Therefore 100x is equal to 126 plus x. Now I am shifting the x to the left hand side, then it becomes negative. That is 100 minus x is equal to 126. 100 minus x is, sorry, 100x minus x is 99x is equal to 126. We have to find x. That is the P by Q form of 1.27 bar. That is x is equal to 126 by 99. This is the rational form of 1.27 bar. Like the similar way, we can write the P by Q form of non-terminating recurring expansions. I think it is clear to you. This is the decimal expansion form, terminating and non-terminating recurring. If we put a bar above a number, then it means that the number is repeating again and again. And by this problem, we will find how a non-terminating decimal expansion form is written in P by Q form. Here in 1.27 bar, 27 is repeating again and again. But we can write it in the form P by Q, that is 126 by 99. That means it is in the form of, we can write it is in the rational form. You are getting questions from this section as express 1.27 bar in the form P by Q, or express in the rational form, or 0.3 bar in the rational form, or any other number in the rational form. The method of solving this is same. Just listen carefully and study carefully how to solve this. I think it is clear to you. Now, moving to the next topic, that is representing real numbers on a number line. Representing real numbers on a number line. How we can represent a real number on a number line? Just by solving one or two questions, I will show how we can represent a real number on a number line. Visualize. Visualize 2.565 in a number line. We have to visualize 2.565 in a number line. How will we visualize 2.565 in a number line? We can easily find 2.5 in a number line. Then the problem is that we are having 3 places after decimal, that is 2.565. Is it possible to represent this in a number line? Just think, is it possible? The first answer came to your mind is that how will we represent this in a number line? We can represent 2.5. That's okay. Then 2.565. How will we do it? Yes, we can do it. First of all, I am considering a number line. 0, 1, 2, 3, 4, etc. This 2.565 is in between 2 and 3. So I am representing only 2 and 3 in this number line. Just for a sample, this is the number line. Okay, just for a sample, I draw a number line here. 2.565. That is 2.565 lies between 2 and 3. Therefore, I have to zoom the position of 2 and 3 in the number line. So I am drawing 2 and 3 in the number line as a bigger portion. This is 2 and this is 3. Now, in between 2 and 3, there is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8 and 2.9. Then it comes 3. That means in between 2 and 3, we are having 10 divisions, 2.1 to 2.9. Now, which is the number we needed? It is 2.565. It is 2.565. Then we are having 2.5 and 2.6. We are having here the 2.5 and here the 2.6. Now we need to zoom the position of 2.5 and 2.6 again. Now we need to zoom the position of 2.5 and 2.6 again. So I am zooming only the positions of 2.5 and 2.6 in the number line. This is 2.5. In between 2.5 and 2.6, there is 2.51, 2.52, 2.53, 2.54, 2.55, 2.56, 2.57, 2.58, 2.59 and 2.6. And the number we want to visualize is 2.565. 2.565. Now we have 2.51, 52, 53, 54, 55, 56, 57, 58, 59 and 2.6. Where is 2.565 located? It is in between 2.56 and 2.57. It is in between 2.56 and 2.57. So again we want to zoom the positions of 2.56 and 2.57. I am going to zoom the positions of 2.56 and 2.57. Here it is 2.56. It is 2.57 and 2.561, 2.562, 2.563, 2.564, 2.565, 2.566, 2.567, 2.568, 2.569 and 2.57. Clear? In between 2.56 and 2.57 there is 2.561, 2.562, 2.563, 2.564, 2.565, 566, 567, 568, 569. Which is the number we needed? It is 2.565. Look, here it is 2.565. Thus, we can locate a number in a number line, a real number in a number line. Thus, look, 2.565 is located. How? First of all, in a number line, we want to find where the position of 2.565. As a basic, we know that it is in between 2 and 3. Therefore, other positions are eliminated and we are zooming the position for 2 and 3. Then in between 2 and 3, there is 2.1 to 2.9. Thus, we find 2.565 lies between 2.5 and 2.6. Then other positions are eliminated and we are zooming 2.5 and 2.6. Again, in between 2.5 and 2.6, there is 2.51 to 2.59. Then we know that 2.565 lies between 2.56 and 2.57. Again, zooming the positions of 2.56 and 2.57, we get 2.561, 2.562 up to 2.569. Then we get the answer 2.565. Okay. Thus, we visualize 2.565 in a number line. Okay. Now, we can solve one more. We can solve one more in the same pattern. If there is any confusion in the first question, then listen carefully to the second one. Now it becomes easy for you. Visualize 3.421 in a number line. This is the question. Visualize 3.421 in a number line. And our basic number line is 0, 1, 2, 3, 4, etc. -1, -2, -3, etc. We want to visualize 3.421. This 3.421 lies between 3 and 4. This 3.421 lies between 3 and 4. So we have to zoom the positions of 3 and 4. I am zooming the positions of 3 and 4. In between 3 and 4, there is 3.1, 3.2, 3.3, 3.4, 3.5, 3.6, 3.7, 3.8, 3.9 and 4. Now the number we want to visualize is 3.421. 3.421. That means that is in between 3.4 and 3.5. That is in between 3.4 and 3.5. So we have to zoom the positions of 3.4 and 3.5. We have to zoom the positions of 3.4 and 3.5. In between 3.4 and 3.5, there is 3.41, 3.42, 3.43, 3.44, 3.45, 3.46, 3.47, 3.48, 3.49 and 3.5. Now again look, which number we want to locate? 3.421. 3.421. This 3.421 lies in between 3.42 and 3.43. So again we want to zoom the positions of 3.42 and 3.43. 3.42, 3.43. In between 3.42 and 3.43 there is 3.421, 3.422, 3.423, 3.424, 3.425, 3.426, 3.427, 3.428, 3.429 and 3.43. Now look, if there is the number we want to visualize, yes, it is here, 3.421. Here it is, 3.421. Thus, this is the position of 3.421 in the number line. Thus, we can visualize any real number in a number line like the same way. Just first of all, you have to identify the number lies in between two numbers. Then zoom that position. Again divide it into 10 positions. Thus by zooming again and again, we can locate or visualize the given number in a number line. I think now it's clear to you. Moving to the next topic, operations on real numbers. We are having different types of operation: addition, subtraction, multiplication, division, rationalizing, etc. We can go through some problems and how these problems can be solved, and we can look how we solve the problems. The first one is, first problem that we have to solve is 2 root 2 plus 5 root 3 plus root 2 minus 3 root 3. How we can solve this? Similar terms can be added or subtracted. Therefore, root 2 terms should be nearby side. That is 2 root 2 plus root 2. Just rearranging, we get plus 5 root 3 minus 3 root 3. Then look, 2 root 2 plus root 2. 2 root 2 plus root 2 gives 3 root 2. Then 5 root 3 minus 3 root 3 gives 2 root 3. That is, the final answer is 3 root 2 plus 2 root 3. This is the addition. Okay. Now, moving to the next question. 6 root 5 into 2 root 5. This is multiplication. This can be simply done as 6 into 2 into root 5 into root 5. That is equal to 6 into 2, 12. Root 5 into root 5, it is 5. Root 5 into root 5, it is 5. That is 12 into 5, it is 60. The final answer is 60. 6 root 5 into 2 root 5, that is 6 into 2, 12. Root 5 into root 5, 5. That is 12 into 5, it is 60. Now next is 8 root 15 divided by 2 root 3. Now in this question, 8 root 15 is rearranged as 8 root 3 into root 5. Root 3 into root 5 is root 15, 8 is there. Then no change for the value, remains as the same 8 root 15 all divided by 2 root 3. That can be written as 8 root 3 divided by 2 root 3 into root 5. Here in numerator and denominator root 3 is there and we can cancel the root 3. Then 8 divided by 2 is here, 8 divided by 2 is 4, then into root 5, that is 4 root 5. Here the final answer is 4 root 5. The next question is 5 plus root 5 into 5 minus root 5. Look, in this question, 5 plus root 5 into 5 minus root 5. This is of the form a plus b into a minus b. This is of the form a plus b into a minus b. This is a standard result. A plus b into a minus b is equal to a square minus b square. A plus b into a minus b is equal to a square minus b square. Here in this problem, in place of a it is 5 and in place of b it is root 5. Therefore 5 plus root 5 into 5 minus root 5 can be written as 5 square minus root 5 the whole square. That is equal to 5 square is 25 minus root 5 the whole square. Root 5 the whole square is 5. That is 25 minus 5 gives 20. The final answer is 20. Remember the result, a plus b into a minus b is equal to a square minus b square. Now moving to the next question. Rationalize the denominator. Rationalize 1 by 2 plus root 3. This means that rationalize the denominator 1 by 2 plus root 3. You are having questions, rationalize the denominator. Rationalize 1 by 2 plus root 3. How we could rationalize this? Just listen carefully. 1 by 2 plus root 3. Same is written as. Then to rationalize, we have to multiply. Here it is 2 plus root 3. Then we have to multiply by 2 minus root 3. Just changing the sign. If it is negative, then multiply with the positive. If it is positive, then multiply with the negative. By 2 minus root 3. In numerator and denominator. If 2 plus root 3 is here, then multiply with 2 minus root 3 in the numerator and denominator. If 2 minus root 3 is here, then multiply with 2 plus root 3 in the numerator and denominator. Thus, 1 by 2 plus root 3 into 2 minus root 3 by 2 minus root 3. Then 1 into 2 minus root 3 gives 2 minus root 3 whole divided by 2 plus root 3 into 2 minus root 3. That is a plus b into a minus b. Now, I say the result as a plus b into a minus b as a square minus b square. That is 2 square minus root 3 the whole square. That is equal to 2 minus root 3 whole divided by 2 square it is 4 minus root 3 the whole square. Root 3 the whole square it is 3. That is equal to 2 minus root 3 whole divided by 4 minus 3 is 1. Since the denominator is 1, we can write the final answer as 2 minus root 3. Final answer as 2 minus root 3. Clear? Moving to the next question. Same method, rationalize 5 by root 3 minus root 5. like the same way we did before, 5 by root 3 minus root 5. Multiply it with root 3 plus root 5 in the numerator and denominator. Root 3 plus root 5 by root 3 plus root 5. In numerator, 5 into root 3 plus root 5, that is 5 into root 3, it is 5 root 3 plus 5 into root 5, it is 5 root 5 whole divided by root 3 minus root 5 into root 3 plus root 5, that is a minus b into a plus b, and can be written as a square minus b square, that is root 3 the whole square minus root 5 the whole square, that is equal to 5 root 3 minus 5 root 5 whole divided by root 3 the whole square, it is 3 minus root 5 the whole square, it is 5. Okay, root 3 the whole square, it is 3 minus root 5 the whole square, it is 5, that is equal to 5 can be taken as common from the numerator, then 5 into root 3 minus root 5 whole divided by 3 minus 5, it is minus 2. Then I am putting this negative sign in numerator, then we can write minus 5 by 2 into root 3 minus root 5. Minus 5 by 2 into root 3 minus root 5. This is the final answer. Clear? Now we can solve one more problem from the same section. Same, rationalize 1 by root 7 minus 2. Same method. We can write 1 by root 7 minus 2. For rationalizing, multiply it with root 7 plus 2 in the numerator and in the denominator. In numerator, it is 1 into root 7 plus 2 remains as root 7 plus 2 divided by, in denominator, root 7 minus 2 into root 7 plus 2, a minus b into a plus b can be written as a square minus b square, that is root 7 the whole square minus 2 square, that is equal to root 7 plus 2 whole divided by root 7 the whole square, it becomes 7 minus 2 square, it becomes 4, that is root 7 plus 2 divided by 7 minus 4, it is 3. This is the final answer. Clear? Now we go through operations on real numbers, that is multiplication, addition, division, rationalizing the denominators. Like the similar way we did, you can solve all the problems related to the operations. In your textbook, there are lots of problems regarding the operations on real numbers, that is addition, multiplication, subtraction or division, rationalizing the denominator. I solved some questions from that topic. Then you can solve the remaining in your own way, such that what you understand from these solutions. All the method is same, only numericals are changing. So you can solve the remaining in your textbook like the similar way we did. I think it is clear to you. Moving to the last topic of this chapter, we are having some identities. First of all, I have to explain the identities in this topic, and then we can solve some problems using that identities. I'm writing the identity. The first one is a raised to m into a raised to n is equal to a raised to m plus n. This is the first one. A raised to m into a raised to n is equal to a raised to m plus n. Second is a raised to m divided by a raised to n is equal to a raised to m minus n. And the third one is a raised to m the whole raised to n is equal to a raised to mn. And the last one is a raised to m into b raised to m is equal to ab the whole raised to m. Study these four identities, very important one, and this is very useful for your future math studies. This can be used in physics also. We are using these identities. So for solving problems, you must study these four identities. Simple, very simple. Just listen carefully. A raised to m into a raised to n is equal to a raised to m plus n. A raised to m by a raised to n is equal to a raised to m minus n. And a raised to m the whole raised to n is equal to a raised to m into n. And a raised to m into b raised to m is equal to ab the whole raised to m. These are the four identities we are using to solve problems in this section. Now we can solve some problems. First one is simplify 64 raised to 1 by 2. Simplify 64 raised to 1 by 2. How we can solve this? 64, we know that 8 into 8 is 64, right? That is 8 into 8 means 8 square. 8 square is 64. Therefore, I am writing 64 as 8 square. Then the whole raised to 1 by 2. Now look at these four identities. Any one relates to that condition. 8 square the whole raised to 1 by 2. Yes, here it is. A raised to m the whole raised to n is a raised to mn. Therefore, 8 square the whole raised to 1 by 2 can be written as 8 raised to 2 into 1 by 2. Thus, we can write 8 raised to 2 into 1 by 2. 2 into 1 by 2 is 1. Therefore, the final answer is 8. 64 raised to 1 by 2 is 8. You got it? Then, our next question is next is 125 the whole raised to 1 by 3. 125 the whole raised to 1 by 3. 125 can be written as 5 into 5 into 5, right? 5 into 5, 25. 25 into 5, 125. 5 into 5 into 5, that means 5 cube. Now, I write 125 as 5 cube, the whole raised to 1 by 3. The same result we can apply here. A raised to m the whole raised to n is a raised to mn, that is 5 raised to 3 into 1 by 3. That is equal to 3 into 1 by 3 is 1. Therefore, the answer is 5. Clear? Moving to the next question. Moving to the next question, it is simplify 7 raised to 1 by 2 into 8 raised to 1 by 2. Is there any similarity with any results we have written in the left side? Yes, it is a raised to m into a raised to n. It is a raised to m plus n. No, no. This result cannot be used because a raised to m into a raised to n. So, a raised to m into b raised to m is equal to ab the whole raised to m. This result can be used. A raised to m into b raised to m is equal to ab the whole raised to m. Therefore, we can write 7 into 8 the whole raised to 1 by 2. Right? 7 into 8 the whole raised to 1 by 2. And 7 into 8 is 56 the whole raised to 1 by 2. This is the answer. 7 raised to 1 by 2 into 8 raised to 1 by 2. Clear? 7 into 8 the whole raised to 1 by 2. That is a raised to m into b raised to m. In place of a here 7 and in place of b here 8. And in place of m it is 1 by 2. Therefore 7 into 8 whole raised to 1 by 2. That is 56 whole raised to 1 by 2. Okay. Moving to the next one. Moving to the next question. It is 2 raised to 2 by 3 2 raised to 2 by 3 into 2 raised to 1 by 5. Now look, anyone resembles with this result? Yes, it is a raised to m into a raised to n. It resembles with a raised to m into a raised to n. A raised to m into a raised to n is a raised to m plus n. Therefore, 2 raised to 2 by 3 into 2 raised to 1 by 5 can be written as 2 raised to 2 by 3 plus 1 by 5. In place of a, here it is 2, and in place of m and n, it is 2 by 3 and 1 by 5 respectively. Now we have to solve 2 by 3 plus 1 by 5. That is equal to 2 raised to 5 into 2, 10 plus 3 into 1, 3 divided by 5 into 3, 15. That is equal to 2 raised to 13 by 15. 2 raised to 13 by 15. 2 raised to 2 by 3 into 2 raised to 1 by 5. That is 2 raised to 2 by 3 plus 1 by 5. By cross multiplying or taking the LCM, we can easily solve. If we are taking the LCM, 5 into 3, 15 is the LCM. Then 5 into 2, 10. 5 into 3, 15. That is 3. 10 plus 3. Then 2 raised to 13 by 15. Clear? Okay. Then to the last question. I can solve one more question from this topic. Then the remaining questions or any other questions from the question bank or from Google or from any other textbook you can solve using this same result, like the same way we did. Next is 9 raised to 3 by 2. Now the 9 can be written as 3 into 3, that is 3 square is 9. Thus I am writing 3 square the whole raised to 3 by 2. That is a raised to m the whole raised to n, that is a raised to mn. That is 3 raised to 2 into 3 by 2. 2 into 3 by 2 is 3. Therefore, 3 cube. That is equal to 3 into 3 into 3. 3 into 3 into 3. 3 into 3, 9. 9 into 3, 27. Final answer is 27. Okay, I think all the results we have covered. No, a raised to m by a raised to n. Not we are covering. So we can go through one more problem. That is 5 raised to 1 by 3 by 5 raised to 7 by 3 by 5 raised to 2 by 3. Look at the problem. 5 raised to 7 by 3 by 5 raised to 2 by 3. It is of the form a raised to m by a raised to n. It is a raised to m minus n. That is 5 raised to 7 by 3 minus 2 by 3. That is 5 raised to 7 minus 2. It is 5. 5 by 3. The answer is 5 raised to 5 by 3. Now we have covered all the 4 results and put it in the problem for solving that. That's how we done with the chapter number system. Now let us recollect what we have studied in this chapter. In this chapter number system, first of all, we go through the classifications of numbers as natural numbers, whole numbers, integers, rational numbers, irrational numbers, real numbers. Then to find number of rational numbers between two numbers, that may be 2 rational numbers, 5 rational numbers, 10 rational numbers in between two numbers. Then in the topic irrational numbers, we studied to locate root 2, root 3, root 5, root 7, etc. on a number line. Then 2.565 or 3.565, like any real number can be visualized on a number line. That's also we discussed. Then operations on real numbers, addition, multiplication, subtraction, division, then rationalizing the denominator. Then using these 4 results, we are solving problems. That's all we are covered in this chapter. I think all the problems are clear to you. Any doubt, just rewind it and see once more. Then you solve the related problems in your textbook and study well. I am Nitishas and thank you for joining me in this section. Let's meet in another day with another section.